Imagine a pool in which we place a system of two pulleys that move a belt to which we attack H plastic balls filled with air that float. Now, we build a waterproof barrier in the middle of the pool and fill the right half with water, leaving the other half dry. When it is completely full, we slowly release the brake on the two pulleys. Little by little, the floats on the right, pushed by the water, begin to rise, while those on the left, attracted by gravity, fall. It's very slow at first, but over time the speed increases until it's sufficient to connect an electric generator, and voila, we have infinite energy. Or maybe not. Humanity has been seeking what I call the holy grail of the first law of thermodynamics since the Middle Ages, the creation of so-called perpetual motion machines. These are objects that, if they existed, would either create energy from nothing, conserve it, or are impossible to operate in our universe. Let's return to our pool. What's happening here? What's the trick? Why don't we all have these generators in our homes? Because we're poor and don't have pools. Jokes aside, not even the wealthiest can escape the first law of thermodynamics. Simply put, and applied in this case, it tells us that the energy of an isolated system neither increases nor decreases. It remains constant. It is conserved. In the example of the pool, which for practical purposes we can consider an isolated system since the sun's energy is negligible, movement, energy, is seemingly appearing out of nowhere, causing it to no longer be constant. Therefore, the first law of thermodynamics makes the existence of this machine impossible. You might say, okay, that's what the theory says, but I don't see why it shouldn't work. Are we facing one of those exceptions that actually work? Well, no. Like 99% of the perpetual motion machines that have been devised, in this specific case, the energy needed to push each float into the water is exactly the same as the buoyant force generated by the water on the ball coming out. Added to this is the friction with the water and air, which would remove energy from the system in the form of heat, just like car brakes heat up when braking. But the human mind's imagination is fascinating, and so many centuries of trying to outsmart Lady Thermodynamics have borne creative fruit, with the creation of amazing inventions that at first glance might seem to work. But they all have the same problem. The energy they seemingly generate is spent elsewhere in the system. This is one of my favorites, a bit different. Supposedly, the large mass of water should push the water with such force that it allows it to reach higher than the original reservoir, creating an infinite and free flow of water, a perpetual motion where you could place a watermill and get infinite energy. The problem here is that the pressure exerted by a piece of water does not depend on its mass or volume, but on the height of the water column. The pressure exerted by this column will allow the water to rise to the height of said column at most, a phenomenon responsible for the existence of artesian wells, sudden water eruptions in dry places without nearby lakes or rivers. What we have here is an aquifer, a mass of water trapped between rocks whose maximum reservoir height is higher than where we are. If we drill the rock, the water will reach the maximum height of the water column, which will slowly decrease as we use the water. It will seem like magic and infinite energy, but we'll just be balancing the system. It's fascinating how it seems the universe carefully prevents us from cheating. So all these examples don't work, but we're getting close. If there were no frictions, we could achieve it. As long as we don't extract energy from the systems, the energy would remain, fulfilling the first law, and we would indeed have a perpetual motion machine. But we're surrounded by air, water, and machines with cables, gears, and oil that generate a lot of friction. However, in this universe, there are fascinating exceptions. There's a ball that has been spinning for years without stopping, floating in a vacuum with a very special configuration so that gravity doesn't affect it. It has been doing so for billions of years. However, the Earth is not a perfect perpetual motion machine. It almost is, but not quite, because part of its rotational energy is slowly lost due to the exchange of momentum with the Moon. In other words, tidal energy is not free, and although much more slowly, the Earth's orbit around the Sun is also degrading due to the emission of gravitational waves. So, we could say that Earth is almost a perpetual motion machine, and that almost applies to the rest of the celestial bodies in the cosmos. These are the objects that come closest to a true perpetual motion machine without any almost. In other words, tidal energy is not free, and although much more slowly, the Earth's orbit around the Sun is also degrading due to the emission of gravitational waves. So we could say that Earth is almost a perpetual motion machine, and that almost applies to the rest of the celestial bodies in the cosmos. These are the objects that come closest to a true perpetual motion machine without any almost. We can imagine a more extreme case, like a rogue planet, a type of planet that was ejected from its galaxy and roams intergalactic space. If this planet positioned itself in a very specific zone, halfway between two galaxies, their gravities would cancel out, allowing the planet to stay there without having to orbit them, thus avoiding energy loss in the form of gravitational waves. But this would be like balancing a marble on the tip of a pin. Any disturbance, however small, would destabilize it. For example, mass redistributions within the galaxies could slightly shift the equilibrium point and eventually cause destabilization. You, yourself, with your phone or your arm, are already modifying the center of mass of the Milky Way, causing the pin to wobble just with this. Therefore, really only a photon traveling through a flat and empty universe, or a body rotating in a universe consisting solely of that body, could be considered a true perpetual motion machine. But does a tree make a sound when it falls if no one is there to hear it? What makes a sound is NASA's G2 Flywheel, the closest thing to a perpetual motion machine created by humans. It's an unconventional energy storage system, simply a very heavy wheel spinning very, very fast inside a box with no air, so the friction is almost zero, and therefore you can't hear its noise. There's no air to propagate it. The friction is so low that it takes years for the most precise instruments to detect changes in its speed. This device is essentially a battery, but it stores energy not in chemical bonds, like conventional batteries, but in angular momentum, that is, in rotation. If the wheel's mass and rotational speed are moderately high, these batteries can be much more efficient than conventional ones in terms of occupied volume and total weight. Hence, NASA is considering them as possible batteries of the future. To extract energy from them, you just need to connect a dynamo to the rotation axis, and to store energy, you just need to make it spin faster. Very nice and fascinating. But we came here to talk about how to create infinite energy. Well, perhaps you'd be interested to know that pure vacuum has infinite energy, meaning that even if you manage to isolate a piece of space-time completely, with no atoms and at absolute zero, this vacuum would always have a minimum energy level, the so-called vacuum energy. Although it is quite small, we have been able to extract it. This is known as the Casimir effect, in which two metal plates placed in a box with perfect vacuum attract each other, not due to electromagnetic effects, as they are electrically neutral, nor due to gravity, as they are too small for it to be appreciable. They move due to this vacuum energy, which, simplifying a lot, creates waves of perturbations in the quantum fields that push the two plates together. They join and do not separate because the space between them is very small, and the perturbations that appear between the two plates are much smaller and weaker than those that appear between them and the wall of the container. In a way, we could say that space-time itself is a generator of infinite energy. The problem is that we don't know how to harness it, and we suspect it's impossible. In the case of the Casimir effect, once the two plates have joined and that energy has been harnessed, you need to spend the same amount of energy to separate them again so they can come together once more. The same happens in other experiments that manage to harness vacuum energy. The net energy obtained ends up being zero. This is why many authors consider that vacuum energy can never be harnessed to extract infinite energy, as everything currently indicates it is faithful to the first law of thermodynamics. But hey, a promise is a promise. If you want to get infinite energy, I'll tell you how. And look, it'll be free. You can't complain. Today's tutorial is economical, so you can buy the pool. What you need to do to get infinite energy is simply wait. Wait a bit quite long actually, specifically 10 to the power of 10, to the power of 10 to the power of 56 years, the time needed for quantum tunneling to cause another Big Bang. Assuming the universe is infinite and isotropic, something the evidence seems to indicate. The Big Bang is the only moment in its vast history when when infinite energy was created from nothing. And the most accepted theory currently predicts that there could be infinite Big Bangs, given enough time. If that seems like too long, then in another video we'll see how to build a time machine. Until then, remember that patience is the mother of science. Thank you very much for watching this video, and goodbye.